All right, I thought I'd give my hand a try at some of the problems in the 70s and do some of the collision dynamics type of problems that are kind of fun. 272 talks about a sample of hydrogen iodide molecules. These are actually a very important sample of molecules historically with dynamics. HI were the molecules that a lot of the early work was done on experimentally. But this problem asks us to calculate the mean free path, represented by the lambda, and the collision frequency. Really, it's the binary collision frequency because we're counting the individual numbers of collisions between HI molecules. Let's use the ideal gas law to get the number density, which is an important quantity in these problems. And so let me rearrange the ideal gas law, PV equals nRT, to give me an expression that isolates the number of molecules over the volume. Remember that moles is the number of molecules over Avogadro's number. So if I rearrange this guy, I get this expression. If the pressure is 1 atm, as it's given to us, and Avogadro's number is known, 6.022 times 10 to the 23rd, R is the 0.08206, which we use in the ideal gas law, and the temperature is 300 K. I need to keep in mind that this is going to generate a volume in the denominator here. In other words, 2.446 times 10 to the 22nd molecules per liter. Because the dynamics equations end up using things like kilograms and such because it's in joules, we're going to have to convert that to per cubic meter. So I'll do 1,000 liters over 1 cubic meter, gives me a number density of 2.446 times 10 to the 25th molecules per cubic meter. Usually they don't write molecules in the equation. The mean free path is an equation from the text, which, remember, gives us the distance that a molecule travels on average before it collides with another molecule. So, as you might expect, it's going to be inversely proportional to the number density. So if I plug these guys in here, the square root of 2 times pi, the collision diameter, remember that's not the diameter of the molecule, it's the diameter of the cylinder that the molecule sweeps through space, which yields collisions. So that's a slightly different number. And then I'm going to put it over the value we just calculated above. This is meters to the minus 3. And when that is churned through, I get 3.53 times 10 to the minus 8th meters. On average, that's the distance an HI molecule travels under these conditions before it collides with another molecule. If you want to calculate the what we call the binary collision frequency, I need to get the average speed. Remember, we had 3 different kinds of speeds. We need the average speed in this equation, which is 8RT over pi times the molar mass. This time I'm going to use the energy version of the gas law constant, 8.314, just a reminder, joules per K per mole, times the temperature of 300 K, and I've got a molar mass here. Remember, it's got to be in kilograms, 127.9 times 10 to the minus 3 kilograms per mole, because kilogram is inside the joules. So I have an average speed of 228 meters per second. The binary collision frequency looks like a little bit of a mess. There's a lot of numbers here, but you can do them one at a time. That's the square root of 2 over 2 pi d squared the average speed times the number density squared. I have the square root of 2 over 2 times pi. The collision diameter, that quantity squared. Now I throw in the speed that we just calculated, and then the number density, which was way up from the top. I'm going to round that off a bit, times 10 to the 25th. Meters cubed there. And I need to include a conversion because, again, of the meters cubed relationship with liters. Is that what we were asked for? Not sure why it has to be this way, but if we make the conversion into liters, I get a stunning number of collisions per liter per second. Collisions per liter times seconds. An absolutely huge number. 2.74 looks at a bit of a thought problem where we're going to have to look at two different conditions and set them equal to each other. This is a kind of a made-up case. There's no way you could get a sample of gas to all have exactly the same velocity. But what we're told here is suppose all the helium atoms in a container, you can imagine a balloon, do have exactly the same velocity for a microsecond. They give you the value of 2.74 times 10 to the 4th centimeters per second. After collisions, they're gradually going to turn into a Boltzmann distribution. The question is asking at what temperature will the sample be when the Maxwell-Boltzmann distribution is attained. Here we have to set a couple of quantities to each other. Because these are helium atoms, all the energy is in translation. None of the energy for this sample is going to be in vibrations or rotations or anything else. It's all in translation. And so that makes the math easier. If you have a sample of helium, if you know the number of helium atoms, all you need to do is multiply that times 1/2 mv squared, and you've got the total energy of that system. If you have a Boltzmann distribution of molecules, the total energy of the system is simply the average translational energy of the distribution times the number of molecules. You see that the n drops away, so we end up having 1/2 mv squared is equal to 3/2 Boltzmann constant times temperature. This is the expression for the average kinetic energy of a distribution of molecules. Now we could just solve for T. If I put T all by itself, put mv squared over, what do I want to do here? The 2's cancel, so there's a 3 here, and a Boltzmann constant. Boltzmann constant is 1.381 times 10 to the minus 23 joules per K. I get a very, very cold temperature of 12 degrees Kelvin. That was a bit of a surprise, but that's the way it worked out. Finally, 2.76 asks us to calculate some collision frequencies at two different pressures to see how the pressure affects those values. This one's got quite a bit of math in it. I'll do it for one of the pressures, and I'll rely on you to do it for the other pressure. So this is similar to the problem we did, 272. I'm going to need to calculate the number density because we use that so often in these collision frequency problems. So I've got a pressure of 1 atm. Avogadro's number is 6.022 times 10 to the 23rd. This is a gas law problem, so I'm going to use the gas law constant. And then I need to do 313 Kelvin. That's 40 Celsius converted to Kelvin. That gives me a number density that's in the number of molecules per liter. As we said earlier, because of the ideal gas law, we're going to get liters, although whenever we deal with these, we eventually want to get rid of the liters and have it in meters cubed, so the 1,000 comes in handy. So I get 2.35 times 10 to the 25th, essentially molecules per cubic meter is the way that it's expressed. Just like we did before, the average speed is the version of speed that's used for collision frequencies. And in this expression, similar to before, I use the energy version of the gas constant times my temperature of 313 K, and the molar mass is expressed in kilograms per mole instead of grams like we normally do. And my average speed turns out to be 181.8 meters per second. Remember, the collision frequency, this is the number of collisions that an individual mercury atom hits as it goes through a sample. So that's what Z1 is equal to. That's going to be equal to the square root of 2 times pi times the collision diameter, that's this expression squared, times the speed that we just calculated, times the number density, 2.34 times 10 to the 25th inverse cubic meters. So an individual atom is going to make 3.4 times 10 to the 9th collisions per second. That's an awful lot. The binary collision number is the total number of unique collisions that occur in a sample. That reduces to 1/2 times Z1 times the number density. I'm not going to go through all of that again. So I'll just plug in the number that we calculated just above and then multiply it times that number density. And here I get 4.04 times 10 to the 34th. What's interesting, and I'll do it in a different color, when I decrease the pressure and go to 0.1 atmosphere, the collision frequency ends up basically going down to 3.4 times 10 to the 8th, and the binary collision frequency goes down to 4.0 times 10 to the 32nd. So basically that's telling us that this collision frequency value is proportional to pressure, whereas the binary collision frequency is proportional to pressure squared. All right.